It's great to be here at GOSIM. I didn't realize there would be another slide about me before this about me. That's why there's another about me. As was said, I'm a partner at Agalia, and I work on the web platform team. On the web platform team, we work on the implementation of web standards like CSS, HTML, and a variety of different web browsers. And I've had the pleasure to work on many different web browsers, including WebKit, Chrome, Firefox, and others, which I won't mention. But nowadays, I'm working on a project called Servo, and I really love Servo, and I want to talk to you today a little bit about Servo and about web browsers and browser engines in general. So before I get started, I would love to ask if anyone here has contributed code or a test to a web browser or a browser engine. Just raise your hand if you have. I don't see that many hands, which is great, because this talk is for you. The goal of the talk today is to convince you that no matter what kind of developer you are, you can contribute to a web browser. So just to clarify, what is it that I'm meaning when I say browser engine? So the browser engine is the web view part of a web browser, the little bit that actually shows the web contents. And web browsers in general have a browser engine inside them. Maybe you've heard some of these technologies before, but for instance, Chrome has a browser engine called Blink, and WebKit has a browser engine called Safari. Oh, that's flipped around, actually. Safari has a browser engine called WebKit, and Firefox has a browser engine called Gecko. So what isn't in the browser engine then? These are things like the address bar, the bookmarks, the tabs, all the other stuff that goes on inside the browser application. So I know what you're thinking. You're thinking, wait, I know a little bit about browsers. I know that they're really, aren't they just, big and complicated? Well, they are big and complicated, but don't be afraid because they're also modular. This means that they're composed of many different kinds of software components that do different things. So you might be a browser engineer that focuses just on authentication. You might be a browser engineer that just focuses on networking. And you can spend your entire career doing that, working on browsers, but only on one part of the browser. That's how rich the browser space is, and that means they're more accessible to you because you might just focus on one thing. You don't need to focus on the entire browser when you're working. The other thing about browsers is that they're incredibly well tested. What that means is that when you make a change, you run a huge suite of tests, and if you made a small mistake, it'll probably catch your mistake. And if you made a small mistake and it didn't catch your mistake, you get to write a test. So that just makes us feel a little bit more comfortable working on these big, complex pieces of software. The other thing is that browsers are accessible to different experience levels. Believe it or not, some people got their start in open source working on big, complicated web browsers because they worked on one specific part of it, and they gradually learned more about the space, and that became their full-time career. So all that to say, with a little bit of dedication and some willingness to learn, all of you can work on the web platform, on maybe the most complex piece of software that we use in our day-to-day life. So I just want to get started with some basic definitions. And sorry if you know all these things, but I think it's good to start at the beginning. So this is a web browser, or a crude drawing of one. What we see here is that, like I explained before, the browser is the whole window with the address bar, the back and forward buttons, the tabs. That's all the browser. But just that content piece is the browser engine. If we zoom into that content piece, we see that the main document is called the main frame. And this is a term that comes, I don't know if you remember this old feature in HTML called frames. They predate iframes. But this is one document, one HTML file, say. And if you have an iframe inside, that's called a subframe. And each of these two things is a separate world, say. And you may or may not be able to communicate between them depending on security restrictions. But you can kind of think of each of these as a separate universe of API calls and data that are isolated from each other. So a typical browser engine is written in C++. All the major browser engines are written in C++, which means, this is important, which means that they have a lot of memory errors. You have to be careful when you use pointers. It's easy to shoot yourself in the foot and cause a crash. And all of these crashes can expose your users to terrible security situations. They can lose their bank account information. So they're like the most important kinds of crashes to avoid, written in one of the worst languages to avoid crashes. Browsers, some of them are older, but browsers are around 20 years old. This means that they're legacy pieces of software. They have a big history to them. It takes if you do git log, it takes a really long time to get to the bottom, like minutes you might wait for your terminal to get to the bottom. And they're made up of many different components. Like I was saying before, there are many different modules. You can think maybe a good analogy to a browser is a little operating system. It exposes lots of platform APIs. It has different concerns. They all come together in the browser. Something unique about browsers compared to other software, except maybe Windows as a concept, the operating system, I mean, is that they have to handle a huge variety of content. And in particular, there's over 30 years of content that the browser has to be backwards compatible with. And also, there are millions of users creating new content for your browser that's going to stress it in different ways. And a not insignificant portion of those users are malicious. They're trying to break your browser. They're trying to steal data from your users. So you have to take all that into consideration when you're working on a browser. Thankfully, there are tests. But what this means is that everything is security critical in a browser. Every library that you use, every small utility function, every font that you download, all this stuff. You have to think about it and imagine that maybe it's malicious or it's being used in a malicious way. Another interesting thing about browsers is that they are multi-process and they're multi-threaded. So browsers are multi-process in the sense these days that different tabs or collections of different tabs and iframes are running in different processes in order for a couple of reasons. One is security. If you manage to take over one page, it's much harder to cross an interprocess communication boundary and take over another one. So there is some security benefit to this. The other thing is, if a page triggers a bug and crashes, it's not going to bring down your entire web browser. These were things that were that came about in Chrome quite a long time ago and now are standard in browsers. The other thing is that browsers run in multiple threads. This takes different forms, and I'll talk about this a bit later. But in general, each process has a bunch of threads going on doing different things. And one of the areas in which this isn't happening is in the DOM and also layout. These have to happen synchronously because the specification depends on that, and all the web pages that are written depend on things happening in a synchronous way. So we can't add as much asynchronous behavior as we'd like in a normal application because that's just the model of the web. So the caveat here is that Servo is a little bit different, and that's why it's really exciting to me. Essentially, Servo is an embeddable, independent, memory-safe, modular, and parallel web rendering engine. And breaking that down a little, Servo is written in Rust. And I'm sure you've seen some of the other Rust talks here. You're familiar with Rust. You know that Rust compiler comes with memory safety guarantees. It prevents you from using memory in the wrong way, multiple mutable borrows, for instance. And the fact that Servo is written in Rust means that it gets all of these benefits. So Servo is a young browser. It's only 10 years old, roughly, which seems old, but again is young for a browser. And all this memory safety from Rust you get without a garbage collector. So essentially, the overhead to it is quite small. Whereas in other browsers, if they take on some of these memory safety tasks, they might have to pay the cost of runtime checking. The other interesting feature of Rust, which I'm sure you've heard people talk about this week, these last 2 days, are that it includes a lot of really great concurrency primitives, which means that combined with the memory safety system, these primitives allow you to spread the work across multiple cores without worrying about the interaction of the cores, accessing the memory, writing to the same memory. Rust is basically keeping you safe from all these kinds of problems. Servo has both a multi-process and a single process mode, and you can switch between them using a command line flag. The single process mode, like in some other browsers, is useful for debugging, useful for testing the behavior, but it also has multi-process capabilities. Servo is a bit unique compared to other browsers. A lot of other browsers, they build everything in. So like, it's difficult to take out one piece of the browser and use it somewhere else. But Servo is one of the older big Rust projects that's still around. So over the years, it's developed a series of crates that are used by other Rust projects. And it uses a lot of crates from the Rust community as well. One interesting example of this is that the style system and the rasterizer in Servo are shared between Servo and Firefox. And essentially, this works just fine. And it means that it proves that like this modular approach to writing Rust components pays off in the end because both Firefox and Servo get all the benefits of the work by the two communities. And finally, interesting for our talk, Servo is easy to hack on. It's pretty small for a web browser. It's not small, but it's small for a web browser. And the code is newer. It's a bit easier to follow why decisions were made. So for me, at least, I've worked on a bunch of different web browsers. I find Servo pretty easy to get into compared to some of the other ones. And I think that's great. I think that means that Servo has an opportunity to attract work by people that other browsers might not normally have work on them. So I want to kind of get into what makes a web browser. I mentioned that web browsers are composed of different components. So some of these components are a network stack, an HTML parser, a CSS parser and selector, a JavaScript engine and DOM, a style engine, a layout engine, paint and composite. This feels like a lot of things. This is only some of the components of a web browser. But when we start looking at these things, they start to make sense. So for instance, the network stack. What this part of the browser engine does is that it's responsible for opening up a socket to servers and communicating with them. It often knows, well, these days it must know how to speak TLS in order to securely communicate with servers. And then one of the first things it does is it parses and produces HTTP headers that wrap the content that web browsers serve and also the requests they receive. This networking component almost universally in browsers deals with two big objects: a response, which is essentially what you get back from a web server when you've made a request, and a request object, which represents the request that you're going to make to the server. These objects contain things like the method, if you have extra data that you're sending, and the data that you receive back, which might be the source code of an HTML page. An important piece of the networking stack is that it must know about MIME types, which is essentially how the server is communicating what the data that you're receiving is. And it must know how to handle HTTP authentication. As long as that's still around, you'll need to be able to authenticate yourself using the HTTP protocol. When we think of networking, we often think of loading the content into the mainframe. But a lot is going on when we load that content. For instance, if that content contains iframes, that's another load that's triggered. That also goes to the networking stack. If the content contains images or media, those have to be loaded. If the content is JavaScript and it makes a fetch call or an old XML HTTP request, that also goes to the networking stack. And finally, WebSockets are often inside of the networking code as well. This WebSockets piece usually has its own behavior, unlike all the other ones, which more or less follow the same HTTP pattern. But in general, this WebSocket implementation is usually put inside the networking stack. This is kind of like where the data comes from in the web browser. The next logical place to look would be the HTML parser. And this is responsible for turning the source code of an HTML document into a DOM. So it takes each of these tags and creates a tree structure, which is represented in memory as a tree, which is what you access when you call DOM methods in JavaScript. And essentially, the parser is doing this transformation. So in general, I would say that HTTP parsing, HTML parsing, follows the HTML5 parsing specification nowadays. Before HTML5, there wasn't really a good specification for HTML. And there was a lot of different browser behavior when it came to things like if you forgot to close a tag. Different browsers might do different things. What's great about the HTML5 specification is that it gives an algorithm for processing any kind of HTML, no matter if it has errors or if it doesn't, if it's perfect. It tells you what to do in any situation. What this means is that all browsers basically have the same parser. The specification is essentially an algorithm written down, which can be good or bad, but in this case, it's great because all the browsers are completely interoperable when they're parsing HTML. The other great thing about HTML5 is that as opposed to some other specifications, like what's it called, XHTML, which was a sort of aborted specification from the mid-2000s, which had to be valid XML. HTML5 is completely backwards compatible with content on the web. So it properly deals with this 30 years of content, and it displays it. Still, there are times that we encounter XML on the web. There might be an XML, was it XHTTP document? No, sorry, XHTML, that's right. An XHTML document on the web, or you might have an SVG file, or even a nested SVG file in your HTML document. So the HTML parser has to worry about these things as well, although typically it delegates to an XML parser to handle that kind of work. The way this works, generally speaking, is the bytes come in from the network. They go into the parser. The parser is producing a DOM as it runs through the document. At certain times, the parser has to stop. You may have noticed this if you're writing a web page. If you put a script tag in and you don't tell the script tag that you don't want to wait, it will load the contents of the script, and the parsing will stop. The script will execute, and then the parsing will continue. So it's a little bit more complex than a normal parser, just because it has this streaming behavior, and maybe there are pauses. Browsers can choose to speculatively produce a DOM as it's executing the script tag, and then decide to undo it if the script tag executes body document.body equals, for instance, which completely changes the HTML content of the document. This is handled by a crate in Servo called HTML5ever, which is one of these crates. I've highlighted this one because it's one of these ones that's extremely useful outside of Servo and has a lot of people using it. So this is one area where we feel like Servo is being a good community member and sort of sharing the load of a sort of standard piece of software that lots of different other software can use. So logically, if we continue down this path, I mentioned script tags. To execute script, we need a JavaScript engine. And that's exactly what the exactly what the JavaScript engine does. It executes scripts. These used to be simpler pieces of software back in the early days of the web, but now they are fully fledged compilers, but compilers that respond to the behavior in the code. What this means is that there are different so-called tiers in the JavaScript engine. For instance, one tier might be a simple interpreter, which operates exactly like a JavaScript engine did. Well, exactly no, but similar to the way a JavaScript engine operated back in the early days of the web. But if it notices, for instance, that you're calling a function over and over again, it might decide, hey, it's better if we turn this function into machine code. So it uses a just-in-time compiler to convert the JavaScript into machine code, caches it locally, and now it can execute faster. And I put 2 tiers here, but I mean, I believe some JavaScript engines have 6 tiers. Different levels of optimization they can do to the code, different stops on the path from interpreting to fully optimized code that you might get from a C compiler, for instance. Like the browser engine themselves, browsers have different JavaScript engines, and they all have different names. Maybe you've heard of some of these. In WebKit, the JavaScript engine is called JavaScript Core. In Chrome, the JavaScript engine is called V8. In Gecko and Servo, the JavaScript engine is SpiderMonkey. And I told a little lie earlier when I said that Servo was written in Rust. It is written in Rust. Right now, the JavaScript engine is SpiderMonkey, which is written in C++. So a browser is complex, and even a project like Servo will at times use C++ code. In particular, a JavaScript engine is very complex. It can produce machine code with the JIT. So right now, which is by definition unsafe, because you're executing memory that you're writing to. So it's still an open question of how much Rust can benefit the procedure of writing a JavaScript engine. An experiment for another time, probably. What Servo does is that it has Rust bindings around the SpiderMonkey API in a project called Moz.js. This JavaScript engine is more or less responsible for containing the DOM. At the heart, the DOM, if you ever wondered like what's going on underneath the covers with the DOM, is that it's native objects. So in the case of Servo, these are Rust objects that are exposed to script, usually through a foreign function interface that JavaScript engines provide. This FFI is produced, the code to use the FFI is produced usually with engine-specific glue code. What happens is that there are these definition files, these interface definition files called WebIDL, which are part of the DOM specification, part of the HTML specification. And these are processed and turned into the glue code, which exposes the native objects to JavaScript. And this glue code is essentially saying, like, OK, this is a JavaScript object. It has these properties. This property is a function. You can execute it, all that stuff. In Servo, what this looks like is if you look into the components script DOM subdirectory, there are all these Rust files, one for essentially every DOM object. And if you peek into those, you'll see where the Rust part of the implementation of DOM is. Just to sort of recap how this works, again, you have the WebIDLs. They go through a code generator, which is written in Python typically, which takes the WebIDL and produces a bunch of generated glue code, which essentially takes the Rust DOM code and exposes it to the JavaScript engine. And finally, when you're on JavaScript, you can call a function call or access a property, and that property is essentially a proxied Rust object or a C++ object in the case of other web browsers. So now we have DOM, and we've created a DOM from our HTML. To produce the page, we need something else, and that's the style. HTML just has the structure of the page. The style tells us how it looks. And this has its own pipeline as well. The first part of the pipeline is parsing. When you put a style tag in your document or you link to a CSS file in the header, these things, much like script, block the parser. They have to be loaded and processed, unless you, again, tell the browser engine not to do that. And the parser turns that CSS code into selectors and rules. The selectors tell you what elements to apply the rules to. The rules tell you how those elements should look or act. You get the selectors, and the selectors are sort of like, maybe they match multiple elements. So like, in the example I have here of an element with a class called class, we're just selecting the first child. But if I had removed this first child selector, this selector would match all of the list item children of the element with the class. So that's exactly what the selector matching does, is it takes all the selectors and it figures out which elements in the DOM that the rules apply to. The selector language is very flexible. You could match every element on the page. You could write rules that are really complex, that have performance cliffs. So the performance of the selector is quite critical. It's imperative that the selectors run in a good amount of time, or else the style will take a really long time to process. Finally, we know we have our elements. We have our selectors, which tell us what style applies to those elements. We do something called styling. We finally have enough to do to style them. What this does is that it goes through all the DOM elements and figures out what the final set of rules apply to them. And this is affected by the selectors, but it also might be affected by inheritance, the cascading and the cascading style sheets. So Servo is a bit special. I mentioned that it shared a style engine with Firefox. As far as I know, Stylo is the only parallel style engine. And that's basically because it's written in Rust. And this means that whereas other engines have to go serially through every DOM element to figure out what applies to them, Servo can parallelize that across multiple cores. Yeah. We have our DOM, we have our style. So we know that we have a div, its font size is 30 pixels. Now it's time to figure out what that means spatially. And this happens in a process called layout. And layout is that we essentially are traversing the DOM, looking at the style of each DOM element, and producing something called a render tree. A render tree is essentially, at its heart, is a tree that tells you this is an element, it exists at this place in the page, it has this border maybe, and maybe it's split onto multiple lines. There's a modern approach to this. The traditional approach was quite messy. It had a lot of corner cases, especially when it came to things like breaking things across multiple lines, and very especially when it came to things like breaking things across multiple columns or multiple pages. The modern approach is a multi-step approach, where first you create a box tree. And the box tree is a tree that represents all the DOM nodes before any what's called fragmentation is done. Fragmentation is the process that I was describing before of breaking those elements into multiple lines, multiple columns, multiple pages. Once you have this box tree, you run fragmentation on it. You figure out, OK, this bit of text is longer than its containing block. It needs to be split into multiple lines. And you make a fragment for each of those pieces. And that output is called the fragment tree. And this is the final output in a modern layout system. There are a couple things to consider when we talk about layout. One is incremental layout. You have a page, say. You change the color of the text of one element. It doesn't make sense to completely lay out the page again. In fact, it only makes sense to tweak the color property of that one element. And that process of only doing as little as you need to do is called incremental layout. There's another big piece of this, which is deciding when this changes, what else do I need to change? Am I just changing a color, or am I also changing the size of something? Just changing the size of something, is that going to push other elements around on the page? Did their sizes change? Does it change the way that the lines in that element break? A good incremental layout system will tell you the minimum amount of stuff that you need to run layout on again. The second consideration that I want to highlight is parallelism. So naively, the DOM is easily parallelizable when we're styling it and laying it out. It turns out that's not the case. In particular, the width that something is, the inline size, depending on the writing mode that you're working in, affects its height. Its height affects where other things are laid out. Where other things are laid out may affect their width and their height. So if we were clever, we could figure out a way to run the layout in parallel where we can, and fall back to a serial approach where we can't. No browser engine does this, except Servo. So just a little bit, this will come into handy later when we dive into the code a bit. But Servo's layout is in 2 directories. One is called Layout 2020. This is the modern layout system, although maybe we should update the name. But this is a layout system that properly implements fragmentation, something that a lot of browsers switching to this modern approach have had to do. There's also a legacy layout system in Servo, Layout 2013. That's just because Servo was made before the modern approach to layout. In general, we're only working on the new system. So the way this system works is that there's a top-down DOM traversal, and then as we come back up in that top-down traversal, we collect fragments. And this is, sorry, I guess I should say there's a top-down traversal that creates the box tree, and then we do another top-down traversal on the box tree to create the fragment tree. Parallelism in Servo, as I was talking about before, uses thread pools via Rayon, which do work stealing, to execute the layout in parallel. It's written in a way where a very particular case of this are floats. It runs into a float, for instance. It decides to process that section serially, but notably, when it gets to descendants that aren't affected by the float, it can go back to parallel mode, produce fragments, go back to the serial critical section, go out of the serial critical section, and render the rest of the document in parallel. So essentially, we limit the serial part of layout to just where it's necessary. This behavior can be configured at runtime. This is, again, really useful for testing. You can tell Servo, I only want to run layout on one thread. I want to turn off all parallelism, and then you can get a serial layout again. Useful for testing and useful for testing performance, because this parallel layout maybe isn't always a win. It depends a bit on the shape of your DOM and also the kind of processors that you have in your computer. Unfortunately, the new layout system in Servo still does not support incremental layout, but maybe after this talk, you can help us add that. When we have our fragment tree, this is just a tree which describes the position of elements and how they look. We don't actually have a picture yet. We need to paint that. In most browsers, the way this works, and there are differences, because this is one part where browsers differ quite a bit. In most browsers, what you do is you go through the fragment tree and you collect a list of display items. A display item is a more primitive data structure that describes, okay, this is a box, a rectangle, this is a border, this is a piece of text, and each fragment in the fragment tree might be composed of different display items. The second phase is that we rasterize. So items that need to be turned into bitmaps are turned into bitmaps. An example is all text. All text are essentially fonts, and those fonts describe curves that describe the characters that we want to display. Those characters need to be turned into bitmaps so that they can be displayed on the screen. Another type of rasterization that might need to take place is a section of the display list might need to be rasterized so that it can be passed to the third and final phase, which is the compositing phase. If you've ever applied a filter to an element, if you've ever done a transformation on an element, also some shadows, in fact, those are cases where we need to rasterize the content into a temporary surface, usually, and then composite that temporary surface along with other content. You may be asking, why can't we just, if we're doing a transformation, why can't we just draw them all transformed? Well, it turns out that it matters, especially for something like opacity. If an element has half opacity, and you just drew all the contents of that element separately, you would see that like a stacking set of opaque elements, when really that opacity should apply to all the elements in that subtree equally. And that's essentially why compositing is so important. Servo doesn't do this, but a lot of browser engines do, so I think it's worth mentioning, is that they look at the content on the page, and they say, like, OK, these things are similar, so they should be put into a layer. In your mind, you can think of a layer as one texture on the GPU. And the reason this is done is because in those browsers, if you took a naive approach and just put everything into a texture, you would use too much memory, and there would be too much compositing going on in the GPU. So these browsers have another abstraction to try to like figure out which things go together. I've mentioned the GPU a bunch. Painting involves the GPU almost exclusively nowadays when we talk about rendering the web. GPUs are extremely good, by which I mean fast, at compositing, blending, and filtering. A lot of these things are fairly simple shaders that you can write. So we do things that we can do on the GPU will be much faster there rather than doing them on the CPU. 3D transformations, WebGL, WebGPU, these things are already textures on the GPU. It makes sense that the rest of the pipeline fits in with those things. Otherwise, we're going to be doing expensive readbacks from GPU memory, compositing on the CPU, and then putting it back on the GPU. The performance of this type of approach would be unusable. So we just want to do everything on the GPU that we can when we can do it. So like sometimes we still haven't gotten to the point where we can do everything on the GPU. This is sort of like a weird unsolved problem in GPU programming. You can draw really complex video games where you're like looking at a beautiful waterfall and there's like lens flare. It's sometimes really difficult to draw a simple path on the GPU in a way that's fast enough. So sometimes, depending on your hardware, it may be that things that are arbitrary paths, things that aren't rectangles or, say, a rounded corner, canvas, for instance, sometimes those are still rendered on the CPU and pushed to the GPU in the end. Browsers have different approaches when it comes to putting that content on the GPU. Just a little bit about Servo's rendering, because I think this is also kind of fun. Servo uses a tool called WebRender, which again is shared with Firefox and Gecko. And this is a rendering engine that's really good at just rendering CSS. So things that you can make with CSS, it renders those really fast. It sort of gives up on trying to render arbitrary paths that you can use in Canvas and just focuses on rendering this basic stuff. These are things like text, which are uploaded as atlases to the GPU. It includes things like rectangles, borders, rounded corners on rectangles and borders, shadows, and filters, blending, all that stuff. But before we can pass data to WebRender, we have one final step that we have to do. The CSS specification is large, and there's an appendix at the end, which if you waited till the end to read it, you would be really disappointed, because it tells you that actually we can't render the page content in the order that it was found in the DOM. No, we have to like do it in a very specific order depending on the CSS properties. One property that you might know is a z-index, which completely changes the order that things are rendered. And also things that are more obscure, like does this element form a stacking context? And if you don't know what a stacking context is, I envy you, because it's really complicated. And you'll pull your hair out if you have to deal with them. But this final step essentially just reorders the way things that work. and it does a little bit of grouping to deal with filters and transformations. So this stacking context tree is finally converted into a web render display list. This is the equivalent to the display list I talked about before. We pass that display list to web render. It takes care of producing OpenGL calls for all that display list. And like I said, web render only focuses on CSS, so it doesn't have support for SVG, which, as you know, SVG has paths in it. And it doesn't have support for Canvas. So you're sort of on your own if you're using WebRender. WebRender also takes care of this layerization step that other browsers have to do. It sort of does a bit of that on its own, but not by looking at the DOM, looking at the content that you pass to it in the display list. So it's able to do things that would be more complicated to do in the browser itself, because all the complexities of the web have sort of been stripped away, and it can reorder things and decide, like, okay, I can do these two elements together even though they're in different parts of the display list, but they're not touching, so it works out fine. Like I said, it's written in Rust, and it's shared with Firefox. So again, another piece of software that we're able to share and sort of benefit the community as a whole. So just to recap, this is sort of the flow of data through the web browser. We start with our HTML and our CSS. We combine those once we've parsed them to produce a box tree. That box tree is converted in turn into a fragment tree. The fragment tree is converted into a stacking context tree, which is converted into a display list, which shows up on your screen. Maybe in the process of executing the web page, DOM changes the contents. We have to sort of go back to the second step there and run it again. Or maybe there are event handlers. There's a whole document lifecycle that's also taking place as the web page is executing. So you may be thinking this is incredibly complex. How do we test such a complex piece of software? This is where I give you the good news. There's a lot of tests, a lot of different kinds of tests. So even though it's complex, we're a little bit sure about the changes we make. And let me break this down a little. So at the most shared level, I would say, is this project called the Web Platform Tests. And this is something pretty new in the history of the web. The last 10 years, I think it's really taken off. Before, I'll talk about these a bit later, but before browsers had their own tests, they were all different. It was really difficult to know if browsers did things the same. But these web platform tests are a series of automatically run tests that are shared between all the different browsers. They all have their own test runners that process these tests, and there are 2 million of them. So there's a lot of them. If you want to run them all on your own machine, it will take a while. But we can just run a subset if we know we're changing something in particular. The great thing about this project is that it's not like, you can do this, but it's not like you have to go to the test project and submit a test, and then eventually the browsers get it. No, what happens is you write a change in your browser, so you fix a bug that affected only your browser or it affected all browsers. You add a web platform test to your change. That web platform test is synced to the project, and then later on, all the browser projects pull down the changes to the web platform tests. So there's this sort of building test case archive that benefits all browsers. And also this allows us to compare browsers. If you've ever been to this site called wpt.fyi, you can see how many tests each browser passes. So it's an incredibly valuable project. It makes writing a project like Servo easier. It makes working on a web browser easier, and it's just really great. Before the web platform tests, like I was saying, browsers had browser-specific tests, and they still do. A lot of these tests are legacy tests that stuck around from before the web platform, after the introduction of the web platform tests. And it's just difficult to, if you have 10,000 tests, it's difficult to convert them all to web platform tests. You have to look at each one and know if there's another test for it. You have to convert it, maybe it's written in a different way. And in addition, the web platform test can't test every browser feature yet. There's a test driver which exposes functionality of the browser to the tests. Maybe it allows you to respond to permissions dialogues, things like that. Things that you can't normally do in a browser, but when you're running the test harness, this extra functionality is exposed. Some functionality isn't exposed yet. Some functionality is very difficult to expose. And this is why we have browser-specific tests. But that's not all. Browsers also have typically their own suites of performance tests. These are benchmarks, so you can track performance characteristics of your changes, or also regression tests that make sure that when you make a change, say you deleted this line, I don't know what it was for, it actually was the only thing making sure that this web page didn't render in 2 minutes. And these tests catch those kind of regressions. Unfortunately, there are not many shared browser performance tests. There are some suites, but when it comes to measuring the performance and layout, for instance, it can be quite difficult to do these things just because the test harness isn't advanced enough. Browsers are different enough that we still haven't gotten to the point where performance tests are shared in the general sense. As I was saying before, browsers are security-critical pieces of software. They have to be fuzzed. You never know what kind of content web authors will throw at you, especially malicious web authors. If you don't fuzz your browser, if you don't produce randomly generated documents and just consistently run those documents through your browser to see where they crash, people who are trying to steal data from your users will do that. So in general, all browsers fuzz, and these are used to catch security vulnerabilities. These fuzzers are typically pieces of software that run outside the context of browsers. They're producing documents, then they're fed into the browser, but the fuzzers themselves are generally just software for producing random documents. The last resort for testing are manual tests. Manual tests are just HTML documents that you load in your browser to see if things work. There are still things that are very difficult to test with a test harness. Fewer every day, but some types of user interaction, you really just need to test with a manual test. A prime example of this, I think, is when you specify the cursor that an element should have, the cursor that should appear when you hover over an element, does the cursor change to what you expect? If you take a screenshot of the browser, that cursor is not going to show up, probably. So you don't really know. Also, it looks different on every platform. How do we test that? It's difficult to say. OK, so I did a very quick overview of how a browser engine works. And you may be wondering, OK, that's a lot of information. How do I actually start working on a browser? Well, my recommendation is that you fetch and build Servo. And this is how you do that. Depending on your platform, you might have to follow different build instructions, but they're all listed there. If they don't work for you, just file a bug. It's much easier on Linux than other platforms, like most development tasks. And then you simply run mock build. So I would like to do just a quick, because we're going to sort of dive in here in a second. I'd like to do a quick tour of the different parts of Servo. Generally speaking, everything in the Python directory are build support and scripts. These are things that support the process of building Servo and running tests. Components are where all the Rust, or most of the Rust code lives, different pieces of the engine, different components. And these are just a few of the ones that are listed there. Like I said, Layout 2020 is the layout engine. Then there's also layout thread, which is a driver for the layout engine. This is what communicates with the script, which is where the DOM and the document lifecycles are located. There's a package here called compositor, which is where drawing and input handling happens, style and selectors. In general, these are pretty self-explanatory. Every time you work on a web browser, it involves a bit of code exploration. You have to kind of dig through the code a little bit before you maybe feel comfortable with how all the things connect. This is just part of the process of working on a web browser. The final directory I would like to highlight is this ports directory. These are where the embedding APIs and the applications that use Servo are implemented. When I say application, I mean the little test runner that runs when you boot up Servo. Maybe I can actually show that. I think I have to exit my presentation. Just pull this over. Very difficult to move. So that's some code. So this is me telling the, nope. This is me telling the build system to run the test runner. It'll pop up here in a bit, and I'll sort of show like what this looks like. You may have noticed that I used a program called, this is starting up, that I used a program called mock. I just want to kind of talk about this a little bit. Servo is a Rust project. It uses cargo. Unfortunately, cargo doesn't support all the behaviors that Servo needs. So we have a build tool called mock, which is essentially a series of Python scripts. And this manages setting up the environment for building, which is very important on platforms like Windows. And it also makes running tests a bit more consistent. The only thing I'd say now, if you're going to be hacking on Servo and you're going to use Rust Analyzer, there can be issues with the two of them working together. So I would read the documentation for how to get around those issues. So now that I have gotten Servo running, you can see here that this is the shell that I was talking about. This is essentially a little tiny browser that has Servo inside, and it allows you to test your changes. So you can see that, it's a little browser. All right. So speaking a bit more generally, how do you get started working on a web browser? So there are some requirements. The first requirement is you really should be interested in working on a web browser. It's not the easiest software to work on. Everyone can do it. But if you're not interested in it, I think you'll find that maybe there are more fruitful things to work on. So I would say come in with a lot of interest, because you're going to need a little bit of, the last item, a little bit of grit, a little bit of endurance to sort of get past the learning curve. But once you do, it's very important to have good communication skills and a lot of curiosity, because working on a browser involves a lot of exploration. Some of these things are common to other open source projects, but I think that the web browser really is the exemplary case for where these come into play. Really helpful, knowledge of Git and experience with HTML and CSS. Notice that I didn't write Rust here or C++, and that's because I think it's perfectly reasonable to be able to work on a web browser without writing any systems code. And I'll show a little bit of that in a second. Essentially, if your experience is in QA or front-end development, you're actually in a really great position to work on a web browser because you know either how the web works, you know about CSS, you know about HTML, you've maybe suffered through their quirks, or you know about writing or trying things that break software. And those are two great skills to have to work on the web platform. And in fact, the web platform test is a great place to start working. And again, since the code is shared between all browser engines, you should be able to, if you write a good web platform test, you're going to be improving all browser engines. It's a really great feeling to write a test that breaks in another browser, and then later on, an engineer in that browser fixes the behavior, because you've just made the web a better place for a lot of people just writing a test case, even if you weren't working on that browser to begin with. So usually, these tests are checked in to the browser repository. For instance, in Servo, they're checked into a directory called tests, wpt/tests. This is where they are. And like I was saying, there's a bidirectional sync in this directory with the upstream WPT repository. So if you'd like to contribute to Servo, you can work on the tests, and that code will automatically be synced with other browsers. There are 2 million tests, but there are still many features of the web that aren't tested, especially, let's say, legacy features, or the behavior of a new layout mode when combined with a specific feature of CSS2. These are all things that break between different browsers, and if you have sort of the mind to think of these situations, then you'll be a great contributor to the web platform tests. In addition, there's always room for improvement. The tests can always be better, they can be less flaky, and finally, it's fun to break your browser. It feels like the browser is this piece of software that, it's 30 years old. It's had so many people working on it. Like, how can something simple break? You start playing around, you'll find situations where something simple breaks, something simple looks different between different browsers. It really doesn't take too much to find the pieces of the web that need improvement. Say you're a Python developer. I don't know exactly what all of you work on, but maybe some of you are Python developers. Python is used extensively in browser development. The mock tool that I was mentioning in Servo is written in Python. And almost all browser build tools are written in Python. So if you have Python experience, you can work on that tooling. The DOM bindings generator is written in Python. You can contribute to that. And all the support scripts and test servers in the WPT are written in Python. So there's lots of opportunities for contributing to the web with your experience. And all it takes is going to whatever repository you're interested in and looking for Python issues, looking for issues with the build scripts, look at the labels that are there, and you can find things to work on. If you're a Rust developer, obviously Servo is a Rust project, and there are lots of good first contributions to contributing to Servo. A very simple thing, this is a maintenance task, but it's kind of a nice thing to dip your toe into the process of contributing to the browser, is upgraded dependency. This is a thing that we're always doing. We're always upgrading our dependencies, fixing minor build issues. It's just a piece of life when you are a Rust project. Fix a lint warning, another great starter project, and lots of other types of technical debt. Refactors that need to happen. There's many things. If you're more ambitious, say you want to get started with something more complex, you you can run the web platform tests locally, find tests that fail, and then figure out what code in the browser is implementing that feature, and then write a fix. Simple as that. And I'll show a little bit of that in a second. I want to sort of start out with this idea of porting on legacy tests, though. We'll see how well this works. All right. So I'm going to put my cursor over here. And I'm going to put this over here. So this is Visual Studio Code. Is it big enough to see? Should it be a little bigger, maybe? Actually, I'm going to mirror because it's very difficult to see the screen. Apologies. Maybe before we get started in this code section, does anyone have any questions about this before I dive into the code? Right. Great. All right. So I mentioned that there are tests. And those tests are here in tests, WPT, tests. So these are all the web platform tests. These come from the web platform test repository. So you can see that there are tests here for CSS, for instance. A lot of tests, 2 million. All the different CSS features have tests. I mentioned also legacy tests. In particular, the legacy tests in Servo are stored in this Mozilla directory. And there's one test that I've had my eye on. It's this test in here, and it's really hard to navigate, so I'm just going to use Visual Studio's open file. This test in the Mozilla directory called scroll root. And what this test is doing is that you can see that this test is essentially just an HTML document, and it has a little bit of script here on the onload tag where it scrolls the window by 2,000 pixels. And the title tells me that the test is verifying that scrolling the root does actually do a visual scroll. And we say visual scroll in this case because this is a test called a reference test. What that means is that in the header, we've specified a link, a match, and then a file name of a reference. So if I open this test, I don't know if I can do this. Does it work? I'll do it in the terminal. Oops. If I open this test, you can see that it's fully green. But if it didn't scroll, there would be a red box here. If I open the reference, you can see that it's also fully green. And this is the basic concept of a reference test. We have two HTML files, two source files. When we render them in the browser, the screenshots should be the same. And what this does is this allows us to write a test that doesn't depend on the font size, say, doesn't depend on what fonts are on your system, the way that it renders form controls. We can verify that the output of the test is expected without depending on platform features. And many tests in the web platform tests are written in this style. So there's a couple things that I noticed about this test. One is that it's testing scrolling. But say there was a bug. When I load this, it scrolls to 2,000 pixels. Say there was a bug that meant that the test scrolled to just 1,000 pixels. My behavior is completely broken, but the test is still all green. It still has that functionality. So maybe not only do I port this legacy test to the web platform suite, but maybe I improve it as well. So let's say that instead of having a fully green background, I want to make sure that when I scroll, the element at 2,000 pixels is at the right place on the screen. So I can start modifying this test. And the way that works is I just go here and I say, OK, so I want an element that's at 2,000 pixels. And I'm going to make that element green, because typically a failure in the web platform test is represented as a red element, and a success is represented as a green element. And what I've done is that I've made it so that this element is 10,000 pixels down the page. But let's make it 2,000 so that our scroll is correct still. And then let's reload in Firefox here to see if that worked. Oops, the background is also green, so I need to remove that so I can see the element. So, OK, it didn't work how we expected it to be. We expected to scroll 2,000 pixels down, and the element would be at the top of the screen. Why is that? Well, we can't scroll anymore because the element's at the bottom of the page. So what we need to do is we need to add a little bit of spacing underneath to make sure that this element scrolls to the right place. So we reload. It's there. It's not exactly at 0, 0. That's because by default, the body in HTML has an 8-pixel margin. Just something that you learn when you start working on these tests. So now when we try to run the test that we just changed, and the way that works is you do mock test. WPT is the command, R, because I'm using a release build. And then I believe I can just give it, if this works, it's starting the test server, it's running the tests, and it tells us that our test failed. You can see here that we got a failure, and the reason it's failing is because we did not update the reference yet. So now we need to go through, and we need to go to the reference file, which is alongside this one. It's called scroll root ref. I saw it in the header. And now this is where we have to think. We know what behavior we're testing. We know how this looks. We want to produce a page that looks exactly the same, but that doesn't go down the same behavior path. So we need to think of a way to do that. Well, the output of this test, we know, is a 100 by 100 green rect at 8 pixels. And it turns out that that's exactly the same as if we had this green rect. We put it in the reference file. Let's put a body here. Oops, let's put it here. We remove the background color, which was all green. And then we go take a look at the ref file. And now we can flip between these two. We see that they should be exactly the same. We run the test WPT script again. And our test passed. So now we have improved the test, but it's still a legacy test. Let's figure out how to move this test into the web platform tests so that every browser can benefit from it. Maybe what I do is I go into the test directory. And I poked around a little bit before, so I kind of know where this test is. I looked at the CSS tests, and I noticed that like the scrolling tests, this is very tiny, hey? The scrolling tests are in this directory called CSSOM. What that means is the CSS object model in dash view is related to the view of it. That's the specification usually in CSS that these tests refer to. And in general, most of these tests, what they're doing is they test scrolling by scrolling and then checking the scroll top of the window or where the elements are using the DOM. But this test was specifically about the visual representation after a scroll. So we'd like to keep that property of the test. We could test the location, but maybe there's a bug where the element, when I observe it from the DOM, says it's in the right place, but actually in the display it's not. This might be a bug in the painting part of the browser. And I saw here that there was, I believe, nope, display. Right, there's a series of tests here, one test in particular, called scroll top display change. And if I take a look at scroll top display change, I can see that it's doing something very similar. It has a reference, which means it's comparing the screenshots of the two elements. And that's how it's doing the test. This may seem a bit weird. It may seem a bit drawn out here the way I'm looking at this other test instead of just dropping the test into the directory. But what I'm trying to show here is how one typically works on the web platform tests. It's a good idea to go look in the test directory when you're porting a test to see what else is there, to follow the conventions of the tests in the directory, and to make sure that your new test is fitting in the same way. So one difference here is I notice this one's called scroll top display change. So maybe what I do is I rename this test to be similar so that people know it's similar to the one that already exists, to, let's call it window scroll by display change. Just to say that we're calling window.scrollBy and we're trying to observe a change in the display. Now we also need to change the name of the reference here to window scroll by display change -ref to indicate that it's a reference file. We also need to update the test in the header. Window scroll by display change ref. All right. So now the test is renamed, but it's still not in the WPT suite. So we go to Git. We take a look at our code. And what we do is looks like I had a previous version of this. We move a file. Let's remove these old ones. Risks of live coding. We move these files into the WPT test directory. Oops, bad source. Because it shows up as deleted. Oops. You know what I did? I deleted my... Like I said, anyone can work on the web platform. Save. I've done it. I'm just going to put them in the directory. All right. New tests, I will add them in Git. They still show up, they don't show up as moved, I think because I have to do remove. All right. So theoretically, I should be able to run this new test. This is the root of the WPT tests, CSSOM view, and then the name of our test. What it's saying here is that it can't find a test by this name. So this is sort of the final piece working on the WPT tests. There is a file that tracks every single test called the manifest. You can see it here in the WPT directory. It's here. Manifest. Oops. I've forgotten the name of the file. But essentially, when we make a new test or change any test, we need to update that manifest file. And the way that works is, again, with mock update-wpt. Did not work. Is it update manifest? I believe it's update manifest. Yeah, sorry. Mock update-manifest. And now we see that the manifest file has changed for both test suites, the legacy suite and the new suite. And if we look at the contents of the change, we see that it's essentially just a JSON file that lists the name of the test, nested in a data structure for the directory, and a hash, which records the contents of the test, an equal sign, which means that it's a reference test. So now this test is tracked by the WPT suite, and I should be able to run it. And it passes. So what I've done is I've just added a test to the WPT suite, not really knowing anything about Rust or how to write a web browser. I just knew how web pages work, and I knew a couple commands which differ between the different browsers, but like how to manage these working with the WPT. So I could theoretically like make a change, which I'll do so I can clear my work, migrate, scroll by, commit, migrate test, scroll root to WPT. And that commit is ready to submit to Servo. So maybe you found that example a little boring. Maybe you don't really care much for writing HTML and CSS. Maybe you're like, I want to write some Rust. You know, let's change the browser. Well, the way we change the browser is first by changing the specification. And what that means is say that we are writing a document. Say, I'm making a canvas, say. I want to make the canvas 100, let's say like 400 pixels by, let's say 500. 500 pixels by 200 pixels. Give it a background of gray. And then close the tag. and say I want to paint on that canvas. I might get this wrong. I always have to look this up. I want to give the canvas an ID. Draw in area. We get the canvas. Document, get element by ID. Drawing area. So drawing area. And then I need a context to paint on the canvas. I believe it's drawing area dot get context 2D. We do context dot fill color, say red. Context dot fill rect. And we give it 4 parameters, the location of the rect and its size. So 10, 10, 100, 100, if I have not made a mistake. When I open up Canvas, I have made a mistake. Fill color is not a function. It's fill style. Let's open it here. Fill style, I believe. Nope. Fill style, you assign to fill style. Okay, so we have our canvas. This is all just normal canvas, but now we want to use the new rainbow API, canvas.rainbow.fillRainbow. And now when we try to run this in Servo, it tells us that context.fillRainbow is not a function. Even though fillRainbow is now in the specification, there's no implementation of it in Servo. So we need to do that. And how do we do that? Well, this is my approach. Maybe it's not the best approach, but I think it works for most things. I go to the code search part of Visual Studio and Servo, and I search for canvas. And I notice there's a lot of results. Too many results to sort of get started to understand what's going on here. Even though I've limited my results to component scripts, so I'm not getting any tests, I'm still getting too many results. So I have to think like, well, what is fill rainbow like? It's a lot like fill rect, actually. So maybe if I just search for fill rect, I'll see where the implementation of fill rect is. And now it's a lot easier. I have a lot fewer results here. And I just take a peek at all of these things. I see that there's a link here in canvas state to fill rect. There's another, looks like IPC call, canvas message fill rect. There's a function called fill rect. That seems pretty likely to be something interesting. And it's in a function. It's in a file called canvas rendering context 2d.rs. I noticed that there's also off-screen canvas rendering context 2D that has a fill rect, and then paint rendering context 2D as a fill rect. It kind of looks like these 3 files implement the same interface. And that interface might be this last result here, which is canvas rendering context 2d.webidl. And these are the IDL files that I talked about earlier. These are the interfaces of the DOM. So we're adding a new function called fillRainbow to the DOM. So let's just copy fillRect and make one called fillRainbow. It's going to take the same arguments, x, y, width, and height. And when I compile, I should see what happens. So while I'm doing that, let's take a look at these other pieces. So I kind of know what this one does. This is about rendering to canvases. Off-screen canvases, I know a little bit about the Canvas API. I know that there's an off-screen Canvas API. I'm not really sure what this paint rendering context does. So I go here to fill rect, and I just kind of scroll up. Okay, paint rendering context 2D methods. Still don't have a lot of information. Where is this used? This would be the next thing I would do. Find all references. Okay. Okay, paint rendering context. There's a binding here, right, which is in the generated code. This is the code that's generated from that web IDL. I suspect that this is used for paint worklets, another layout API that's unrelated to Canvas, except in that it exposes the same API. So maybe what I'll do is I'll decide to focus on the implementation in the one file that I sort of knew that I was interacting with, the Canvas rendering context. Take a look at our job again, and it seems that we have an error. What this is telling us is that we added a method to the web IDL, but that method is not in the trait that the IDL generated that we're expected to implement the DOM. It says it's missing the fill rainbow in the implementation. So I guess what we can do is go to the Canvas rendering context and add a fill rainbow function. I just copied the fill rect function. And this is going to be needed in all the implementations of this trait. So I'll come here, and I will copy this one, fill rainbow. This is just going to be a stub, an empty method, because I'm not implementing it yet for all-screen canvas, nor for the paint worklets. All right. So I've done an implementation. The implementation is exactly the same as fill rect now. I'm going to kick off the build, and in the meantime, I'm going to take a look at what we might want to do here. So it seems that what this method is doing, just looking at it, is that it's calling into a data structure called canvas state, and it's calling the fill rect method in canvas state. So maybe what I can do is just reuse, well, it's also taking the current color, and because the fill rainbow method has its own set of colors, I don't want to do that. So I probably need to add a new method to canvas state called fill rainbow. I add that there, and then I follow through here. It's not working because it's quite a big. All right, now I'm into the canvas state data structure. You can see here, canvas state. And I can see now what fill rect is actually doing underneath the covers here. It seems to be creating a drawable rect from the coordinates we're given. And if that drawable rect is not none, basically if there's no error, which I know by looking at the implementation of this function, it seems to be checking the arguments to make sure that they're valid. And if they're valid, then it returns a rectangle. So that's what that does. If the rectangle is valid, it gets the style from the current style, and then it sends a message to the canvas rendering thread to draw a rect with that style. So our fill rainbow function that we're implementing is going to work in a really similar way. But instead of taking the style, we're going to want to create our own styles, one style for every color of the rainbow. And that's going. It looks like I'm missing a fill rainbow still. I need to fix this build error. I just hadn't saved. I have here, ahead of time, gotten all the colors of the rainbow, Roy G. Biv. And I'll just drop them into my new fill rainbow method. So I still need to figure out how to turn these colors into styles, but let's just make an array of them. All right. So now we have an array of all the Roy G. Biv colors of the rainbow. And we like to turn each of these into a style. So we just have to take a look to see what this style is. It seems that it's a fill or a stroke style. We go and look at that, and it looks like fill or stroke can be a color, a linear gradient, a radial gradient, or a surface. In our case, the colors of the rainbows are colors, RGBA values, so we know that we need a list of RGBA colors to create this fill or stroke style. So we go back to where we were, canvas state, and we create RGBA data structures. There is a from floats method on RGBA, which creates an RGBA from the floating point values. So now we have an array of RGBA values. We need to make a little rectangle out of the full area for each of these rainbows, for each of these rainbow sections. So maybe we make an iterator. I think we could do maybe, let's say we want an index for I equals 0 to, can I do color dot length -1. So now we have these indexes. We need to figure out the size of the rectangle for each segment. And so I think we can say, let's say that like each segment is 1/7 of the size of the total size of the rectangle. So like slice height equals height divided by color dot length. Yep. I missed I missed an in. Okay. So now the size of this rectangle, the size and position of this rectangle would be something like slice rect equals the rectangle is here. We're going to reuse this create drawable rect or function. The x value will be the same because all the slices will start at the same horizontal position. The vertical value will be different because we need to offset by all the slices that came before us. So the value will be, I believe, slice height times index. What this means is that the 0th slice will start at 0 at the top of the rectangle, and the next one will start at slice height. The width will be the same because the band will go all the way across, and the height will be slice height. And do that. So now we have the rectangle. We need to get the style for that slice. And we saw that this is just a fill or stroke style here. So fill or stroke style. It's just an enum with a color value, and we give it the color. This should be called colors. Should be called colors. And our index. And then we send that rect. We're going to send the slice rect, not the full rect, and that new style to the canvas rendering thread. And assuming this builds, so one thing about Servo is that the script crate, which is where all the DOM objects are, it takes a little bit of time to compile because there are hundreds of DOM objects. That might be one thing you find frustrating about this. I have made a mistake. I have used index instead of slice index. You don't have to be perfect to work on the web platform, thankfully. So just to recap as this is building, what we did was we changed, this is actually called I. We changed the web IDL, which is the interface that the DOM exposes to the web. That IDL reflects a native Rust code. We had to go and modify the native Rust code for the implementation. But really, like, those are the only two things we did. And the rest of it is really just the complexities of, like, how Canvas works in Servo. So what I was really hoping to express here is there's really not much to this. Really, the most important thing is that you know how this part is supposed to be implemented. And that's domain-specific knowledge. That might be something that's something that you're already doing that is also applicable to the web platform. And you can apply that knowledge directly to a web browser with very little work. I have made a mistake. Yes. So our index is an integer, but we are interacting with floating point values. So we just need to cast slice height. Slice height, and then there, height, color length. This needs to be as F64. So very little time between knowing the DOM API we wanted to change and actually implementing that. Later on, if we wanted to, we could go implement these methods in the off-screen canvas and the paintlet implementation. They basically call into the canvas state, so it would really just be a matter of calling the same function in these files as well to complete the implementation. I've made another mistake. Oh, no, I haven't. I'm good. So it's complaining here because this rectangle is now unused, but we still want to call this because we do want to execute this argument processing code, which verifies that the arguments passed to the Canvas API are what we expect them to be. So I'll just go here and finish the implementation. In this case, we have an inner context, an inner 2D rendering context. That we're just calling into. And once this finishes compiling, we can verify that our change worked. This might be a good time. If you do have any questions, this might be a good time to ask them about anything I'm doing.
Hello. Thank you for the real-time debugging, and it's very nice. And I have a question. So I'm curious about the CSS3 support in Servo.
Yeah, that's a good question. I mentioned that we're rewriting the layout system. There are some elements of CSS3 that we do have support for. Certain types of properties, like I believe things like text transform are CSS3. Those are the kind of things that we will have support for very soon, or do have support for. And also we have a early stage Flexbox implementation. Right now, because we're focusing on this fragmentation piece, we're working a lot on the implementation of basic CSS2 features to handle fragmentation properly, so things like float and tables. But we also have support for some CSS3 properties, which are less complicated right now as well.
So did you run your browser engine against css3test.com or something similar, such scoring the browser engine?
Yeah, so what we do is we run all the WPT tests, and we can see more or less where we stand in relation to other browsers, and basically how much more work we have to do in order to get to a more full-featured state. At the moment, we're focusing on a smaller subset of content, because a browser engine is a huge piece of software, and starting from the beginning means that it's difficult to get to that point in a small amount of time.
Okay, thank you.
还有没有问题？
So
No.
I suppose, well, if there are no other questions at the moment, we can test our changes to see that they do what we expected them to do. Yeah, in general, there's really not sorry. There it goes. So yeah, there's a small, thanks. It was quite a journey, but we got there. There's a small bug, or no, actually we put our rainbow over top. What we did was we put it over top of the other one. That's why that's showing up like that. But yeah, that's how you implement basically any DOM API. All right.